Alright, welcome back again. So last time we ended up drawing the wonderful triangle. And just to double check that works, let's show it. There, beautiful. Everything seems to work, no errors, everything cleans up after itself. Life is indeed good. So the next thing to do is frames in flight. But before that, cheers, bit of iced coffee. Okay, so frames in flight. Right now our render loop has one glaring flaw. We are required to wait on the previous frame to finish before we can start rendering the next, which results in unnecessary idling of the host, meaning the CPU. The way to fix this is to allow multiple frames to be in flight at once. That is to say, allow the rendering of one frame to not interfere with the recording of the next. How do we do this? Any resource that is accessed and modified during rendering must be duplicated. Thus, we need multiple command buffers, semaphores, and fences. In later chapters, we will also be using multiple instances of these resources. Blah 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 blah. Okay. So start by creating a maximum frames in flight member. Although it's a big old const, so let's just chuck it here. Okay, we choose the number 2 because we don't want the CPU to get too far ahead of the GPU. With 2 frames in flight, the CPU and the GPU can be working on their own tasks at the same time. If the CPU finishes early, it will wait for the GPU to finish rendering before submitting more work. Okay, with 3 or more frames in flight, the CPU could get ahead of the GPU. Ooh, that music's a bit loud. Alright, that's fine. Generally, latency isn't desirable, blah, blah, blah. Yeah, okay. So, each frame should have its own command buffer, set of semaphores and fence. Okay, that makes sense. Rename them to change them to a vector or an array for us. Okay, so a command buffer. Command buffer. All of these are actually going to be plurals. So this one, actually if we're recording a command buffer, we don't really care about that. But, okay, that's fine. None of those are all good. That is going to be command buffers. What about this? Yep, that'll also be command buffers. Likely the address of the first one. Oh. Reset command buffers. Oh, we might need to change that function. Alright. For recording command buffer. Ooh. Might have to come back to that. Okay, so this is going to be command buffers as well. Alright, so this function takes in a single command buffer and we're sending it an array of them. And we can't just send it just the first one because we don't know if that's the one we care about. Alright, we'll come back to that. We also need the same thing for image, available semaphores or render finished semaphores and in-flight fences, which are these. Semaphores and fences. Alright. It's going to be a lot of code changes. Then we need to create multiple command buffers. Rename create command buffer to create command buffers. Next, we need to resize the command buffer vector array to the size of max in flight. Alright, let's get back to that, but first, that is going to be called, hang on, oh, it's that one. So this is going to be command buffers. Yep. Okay. And then resize it to this. Okay. Alter the vk command buffer allocate info. Let me copy that. Try and find it. Here you go. It's going to take what's it going to take? Command buffer count to be max in flights, probably. Yep, that's fine. And in our create command buffer, we are going to do a p app command buffers equal to malloc vk command buffer. Oh, size up, sorry. Multiply by max in flights. Yep. Alright, and we're going to cast that to an array of those. Okay, that looks fine. Alloc info command buffer is going to be the size. Alright, let's just double check we're doing that correctly. Yep, that's fine. Although, oh yeah, we already know the size is that constant. Okay, and then VK allocate one takes in the command buffers. We already did that. Okay, that's cool. All right. Now the create synth objects. Sync even. This is where we are doing our semaphores and fences. So create sync objects. Here's the implementation. And what are we doing? Resizing those to be the same as this. Okay. P app. What's the first one called? Image available semaphores equal to malloc size squeeze of. Oh. Multiply by that. What are our image semaphores again? They are these. Whoops. Oh, just a VK semaphore. I probably could have guessed that. Okay, so point to those. Those are image available semaphores, and then similar, same sort of size for render available, render finished. Render finish semaphores. Yep, alright, that's all good. And then also similarly, in flight fences, that's going to be a VK fence. Cool. Alright, so that's everything all allocated. Then, what are we changing here? Probably not much, to be honest. Let me squeeze this down a bit. Passing in the available semaphores at position I. Oh, I say not much, but we actually are. We're going to loop through them and create them individually. So for u32i equal to 0, I is less than faux. It's a bit too gangster. Alright, this is the size. I plus plus. That is actually an int, isn't it? Okay, so then we basically move these function calls into this for loop. And instead of doing this, we actually pass in the I position. But not that up. We actually, there you go. Semaphores at position I, and fence at position I. Fences, sorry. Alright, so that creates the two of everything we need. Alright. And then similarly, in our cleanup, they should be cleaned up in the same way. Oh, so let me just copy that. Just loop through, and then we are done. Remember that there's an S. Okay, and there's our fences. Alright, so we've done the cleanup. Remember, because command buffers are freed. Okay, they're free for us. Okay, that's fine. To use the right object every frame, we need to keep track of the current frame. We will use the frame index for this purpose. Bon, current frame. Okay. Where's that gonna live? Do we need to do that top level, perhaps? Oh, I don't know. Probably top level. Yeah, okay, let's do top level. Alright, so got that, and then we'll just do U32 current frame equal to 0. Okay, so then in our draw for frame, we're going to be drawing, oh, I haven't fixed up all these yet. Ah, yes, that's why. So when we're drawing a frame, we're drawing the specific frame at position current frame. Yep, that makes sense. Semaphores at position current frame. Yeah, and then when we're resetting, it doesn't have any of that in there, but we need to reset the current one too, I believe. Sort of makes sense to me. Yeah, so we're drawing the current frame, we're playing with that indexes of all the stuff we need, the fences, the swapchains, the semaphores, and the command buffers. So yeah, that makes sense. Okay, moving on down, we have our command buffers, P command buffers. We actually, yeah, that makes sense. So we do position that, and our signal semaphores will be the signal semaphores at that position. And then the in-flight fences, same thing. And let's keep moving on down. I think that's probably it. Yeah, okay. Then there's the VKQ submit, which is here. And I think, I think that's all of it. Of course, we shouldn't forget to advance the frame. That's a good point. So at the end of every draw frame function call, we'll do current frame equal to current frame plus 1 with a modulo of the maximum frames, so it never goes over that. Maximum frames in flight. Okay, so if that happens to be 1, that'll be 2, and then modulo of that 2 is 0, so it pops it back to 0. If it's already 0, it plus 1, the modulo of 1 for division by 2 is 1. So we're all good. Oh, that explains it right there. They're using the modulo thing. Okay, we've now implemented all of the needed synchronization to ensure that there are no more than the max frames to be in the queue. Okay, that's cool. Note that it is fine for other parts of the code, like the final cleanup, to rely on more rough synchronization like VK device wait idle. You should decide on which approach to use based on your performance requirements. Okay, to learn more about synchronization, check it out. Alright, let's just check that everything works. Build. Well, it builds. And it runs without any issues. That's cool. Clear. Okay, so jumping back into the swapchain recreation. Okay, the application we now have successfully draw triangle. I can't even read today. But there are some circumstances that isn't handled properly yet. It's possible for the window surface to change, such as the swapchain is no longer compatible. This is like a resize though. Yeah. So if you resize the window, the swapchain has its scissor and whatever the other way, frame or something. and they are measured from some constants that we have at the top of the file. Here, I think. So, well, actually, maybe they come from the glfw window. But either way, if we resize the window, that buggers that swap chain up because it's hard coded. Okay, one of the reasons this could happen is to resize the window. Yeah, okay. Creating the swap chain, create a new recreate swap chain function that calls create swap chain, and all of the create functions for the object that depend on it. Okay, so let's look for create swap chain, and let's just do this, and there it is. I'll do it underneath there. Oh, I'll steal that as well. Create swap chain, recreate swap chain. In that we do our vk device wait idle, passing in our p app device. All right. Then we do create swap chain, passing in the p app, and then create image views, and create frame buffers. So those functions that are called, are they called within the create swap chain? I don't think they are there, no. That is called in the same place they are. So we can do okay, so they all get called once anyway. Right, okay, fair enough. So they get initially called here, and then we're going to call them again when we do recreate. Okay, we first call, yep, that's fine, because just like the last chapter, we shouldn't touch resources when they are still in use. Obviously, we'll have to recreate the swap chain itself. The image views need to be recreated because they are based directly on the swap chain images. Finally, the frame buffers directly depend on the swap chain images, and thus must be recreated as well. Fair enough. To make sure that the old version of these objects is cleaned up before creating them, we should move some of the cleanup code to this separate function that we just, okay. All right, so some cleanup code. Recreate. There it is. Just above there, let's do void cleanup swap chain. It's only used here, so this is the only place we're going to find it. We don't need to do prototype at the top. This will do some cleanup. And we have to call from here, cleanup swap chain. It's likely going to take the same thing as this, because it has to have all the access to things. Okay. Note that we don't recreate the render pass here for simplicity. In theory, it can be possible for the swap chain image format to change during an application's lifetime, e.g. when moving a window from a standalone range to a high dynamic range monitor. Fair enough, yeah, that could happen. This may require the application to recreate the render pass and make sure that the change between dynamic ranges is properly reflected. We'll move the cleanup code for all these objects into the new function that we just created. So, what we used to have in cleanup is we were doing our cleanup for swap chain image buffers and image views and the actual swap chain. So that's that one, and that one, and that one. So let's do that and then move them all into our clean up swap chain function. Yeah, all right, excellent. That's everything I think in there. Yep, that's fine. And then in our cleanup function, we also need to call our cleanup swap chain. Clean up Okay, but where? Oh, right at the top. Okay. So as it turns out, I was wrong. We actually do need to move this up as a prototype because it's being used here. Okay, that's all good. I'll just put it here. Yeah, swapchain. There you go. No errors. No woman, no cry. Okay, I think we've done that. Just check in. Yep, all that remains the same. Now, okay, now that in the choose swapchain extent, we already query the new window resolution to make sure that the swapchain images have the new right size. So there's no need to modify choose swapchain extent. Remember that we already had this. Yeah, okay, so we picked that, use that function to get those values. Okay, that's all it takes to recreate the swapchain. However, the disadvantage of this approach is that we need to stop all rendering before creating the new swapchain. It is possible to create a new swapchain while drawing commands on an image from an old swapchain still in flight, but we probably don't want to do that. You need to pass the previous swapchain to the old swapchain field. Yeah, I do remember seeing that somewhere. I think it was an option that we didn't add in. Yeah. Okay, destroy and destroy. Yes, fine. Suboptimal or out of date swapchain. Now we just need to figure out when swapchain recreation is necessary and call our new recreate swapchain function. Luckily, Vulkan will usually just tell us that the swapchain is no longer adequate during presentation. The VK acquire next image KHR and VKQ present KHR functions can return the following special values to indicate this. Right, so it's going to be here, or where was the other one? Somewhere else. Error out of date. Okay, this swapchain has become incompatible with the surface and can no longer be used for rendering. Usually happens after window resize. Or suboptimal KHR. The swapchain can still be used to successfully present to the surface, but the surface properties are no longer matching exactly. Alright, so we're going to have a result come back from this acquire new image. Okay, VK result. Okay, let's just call it result. So then we can do a check on that to say if result equals VK error out of date KHR, then we want to recreate swapchain, passing in the P app. Else, and return, because we're not going to continue with this function execution. Else, if, there's an if as well. If result doesn't equal VK success, and result doesn't equal VK suboptimal KHR, then we want to throw, but we won't be doing that in C. We'll just quit. And we'll say fail to acquire, if we can spell QIRE. Fail to acquire the swapchain image. And we're going to exit with, what are we going to exit with? What do we got? 16, let's do 17 then. And one day we will definitely tidy that up. If the swapchain turns out to be out of date when attempting to acquire an image, then it is no longer possible to present it. Therefore, we should immediately recreate the swapchain and try again in the next draw frame call. We could also decide to do that swapchain is suboptimal, but I've chosen to proceed anyway. Okay, so let's go. Hey, it's not quite right, but carry on. Fair enough. Now in our queue_present function, we do basically the same thing, which is in the same function call, I believe. Yeah, it is. Okay, so we can't call it result. We'll have to call it something else. Queue result. Yes. Okay. So if queue result equals vk error out of date khr, or result equals suboptimal vk suboptimal khr, then what are we doing? Recreate swapchain, and don't need to return because that's the end of the function pretty much. Actually, we'll be updating that anyway. Otherwise, if vk success does not equal our result, and something real bad has happened. Exit 17 as well, and let's do printf saying fail to present swapchain image. All right. The vk_present function returns the same value with the same meaning. Okay, that's fair enough. Ooh. Nearly spilled my coffee. Fixing a deadlock. If we try to run the code now, it is possible to encounter a deadlock. Ooh, let's try that. Became. Ooh, did we? Well, there's no resizing anyway, so. Nah. Okay, we didn't. But it is possible, apparently. Yeah, let's just run with that. Debugging the code, we find that the application reaches a VK wait for fences, but never continues to pass it. This is because when the VK acquire image, the next image returns the VK error out of date KHR, we recreate the swap chain and then return from the draw frame. Okay. Before that happens, the current frame's fence was waited upon and reset. Since we return immediately, no work is submitted for execution and the fence will never be signaled, causing a VK wait for fences to halt forever. Alright, there's a simple fix, thankfully. Delay resetting the fence until after we know for sure that we will be submitting work with it. Thus, if we return early, the fence is still signaled and VK wait for fences won't deadlock the next time we use the same fence object. Alright. The beginning of the draw frame function looks like this. Okay. Draw frame. Yeah, it does look like that. And what has changed in our request swapchain? Yeah, a bit. Only reset the fence. Okay, so let's do that directly afterwards. P app device 1 P app and 5 fences. Oh, okay, yes, that's fine. Okay, handling resize explicitly. Although many drivers and platforms trigger error out of date automatically after a window resize, it is not guaranteed to happen. That's why we'll add some extra code to also handle resize explicitly. Wouldn't that be two competing code paths? First, add a new member variable that flags that a resize happened. Okay. In-flight fences. Don't know why I searched for that. In-flight fences. Are we gonna really put it on here, or are we gonna? Well, I think it might make sense to put it in the same kind of place as here. I mean, really, all of these struct items could be somewhat global to the file, or actually to the program. I'm gonna just do this because it's good to mix things up every now and then, and this is not a proper project. Frame buffer resize. I just need to, excuse me, just trying to get over that cold, or whatever the hell it was. Okay, so we've got a bool of frame buffer resized, and we're going to set to false initially. All right. The draw frame function should then be modified to check for this flag. Draw frame. Okay. Where? It is important to do this after VK present in our draw frame. Okay. I'll do it here. Wait, what will I do it here? Okay, to ensure the semaphores are in consistent state, otherwise the signal semaphores may never be properly weighted upon. Now to actually detect the resize. Okay. Oh, here we go. It's actually within this if statement. So let's do frame buffer resize is set to false, but we're checking if it is true with an or. All right. Okay, because it's otherwise blah, blah, blah. Now actually to redo the resize, we can use the GLW frame resize callback function in the GLW framework to set up a callback. Okay, init window, where that's defined just below, by the looks of it, static void or just void, and they're all kind of static because it's only one file. Frame buffer resized, no resize callback. My bad. Taking in a GLFW window pointer. The width and height. Int width, int height. Okay, that's cool. The reason that we're creating a static function is as a callback is because GFW does not know how to properly call a member with this. Well, we haven't really got this, so that's fine. Okay. But we do get a reference to the GLFW window. That's cool in the callback, and there is another GLFW function that allows you to store arbitrary pointer inside. So when we set up the window, we could pass it a pointer to something that we might want to use in this callback. That could be useful. Okay. So here we've got the title, width and height, null, null. Set, oh, okay. Not this. Oh, okay, they're using this because they want to pass their the full class around. But we don't want to do that, we just want to pass up p-app. Let's just pass the app and see what happens. Then we also have another call to GLW set frame buffer size callback. God dang, it's so big. Okay. Again, it's going to be that, and now let's, because we actually need this to be there. This is the only place we're calling it, so I reckon let's just throw it here. Excellent. Okay. now, and I try to run the program. Okay, we did that, sorry. There is another case where the swap chain may become out of date, and that is a special kind of window resizing, window minimization. This case is special because it will result in a frame buffer size of 0. Okay, in this tutorial we will handle that by pausing until the window is in the foreground again by extending the create swapchain function. I'm going to delete this because I don't not delete. I'm going to comment it out because I don't think we need it. Do that, and yep, I don't think we actually need that. Set the pointer, but let me just run it again to see. Yeah, that's all good. Didn't need that. Okay, so in our nice. Yes, in this function, we want to recreate the swap chain. Okay, so we're going to get the width and height from the frame buffer, setting it initially to 0. Alright, U32 width, or it might come back as an int. Okay, which is actually the same thing. But hey. Alright, so glfw get frame buffer size, passing in the p app window, and give us the width and height. Or pop it out width and height, please. Okay, while loop, interesting. While width and height. Oh, okay, so this Oh, okay, so we're waiting on events. So if the width and height is 0, or width or height is 0, that somewhat implies that it's been minimized. Then we do the resize, the get frame buffer size, and we wait events. Okay, cool. Width equal to 0. So I'm guessing that when we call this, it sort of defers or waits to do something until the size changes, maybe? I don't know. glfw get frame buffer size, p app again. You know, why don't I just copy that? It's daft. And then glfw wait events. Yeah. Then we continue with the rest of the function call. The initial call to glfw frame buffer size handles the case where the size is already correct, and okay. So if it's already correct, it's fine. And glfw wait events would have nothing to wait on. Congratulations, you finished the very first well-behaved Vulkan program. In the next chapter, we're going to get rid of the hard-coded vertices and vertex shader and actually use a vertex buffer. That's cool. Let's just check everything works fine. Seems to. Ooh. Nice. All right. I'm gonna call it a day there, and so let's do git add main and git commit. What did we do? We handled resize and minimization. American spelling, fair enough. Alright, git push origin main. And that is it. Next time we will look at these vertex buffers. But we're kind of done. Like, we've got a program that uses Vulkan to render and handles resize. Pretty cool. Hope you enjoy.